Hey everyone, my name is Eugene, and today I will be presenting on ischemic strokes, specifically the function that the penumbra has on ischemic strokes. So, taking a look at some strokes, I will be mainly focusing on ischemic strokes, considering that it does account for approximately 85% of all strokes. So, let's take a look at a stroke that occurs here in the proximally occluded MCA. Usually, when a stroke has occurred, the infarct core is being developed, or also known as the infarct core over here. What's interesting is that this infarct core is going to be deprived of both glucose and oxygen. So the question is, how does the body accommodate for that? Well, usually it accommodates for that by developing the penumbra, and the penumbra is actually being developed from the collateral circulation. So if the MCA has been occluded, there's going to be other vessels that are, let's say, coming through the ACA over here, and this will cause the penumbra to basically be supplied, and therefore we can have a new diffusion of glucose and oxygen within the penumbra, but also within some parts of the infarct core. So a big part of this presentation is going to be focusing on the penumbra as well. Taking a look at the evolution of the penumbra, so comparing the ischemic core versus the penumbra core, we know that over time the ischemic core will actually begin to grow, and the penumbra will actually begin to disappear because we have more swelling within the ischemic core. So from hours to days to weeks, so for example from here, from 2 days to 7 days to 17 days, we can see that the core is actually growing in size, and is this red marker right here, while the blue core, which is the penumbra, is also decreasing. So when we take a look at the volumetric evolution, the penumbra is actually going to decrease over the span of 17 days, and the ischemic core is going to climb in terms of its volumetric capacity. We have many times heard the expression that time is brain, and this is usually connected to perfusion. So taking a look at the time frame, in less than 3 hours of last known well, we can consider intravenous thrombolysis with IV alteplase. From 3 to 4.5 hours, there's a weak recommendation of using IV alteplase, and we're going to be transitioning into consideration for mechanical thrombectomy. From 4.5 to 6 hours, there's some harm of receiving IV alteplase, and this therapy may actually outweigh the benefits, and we should begin to assess for mechanical thrombectomy therapy instead. At 6 to 24 hours, the patient is no longer eligible for IV alteplase, and mechanical thrombectomy is usually an option, specifically if there are specialized stroke centers. At more than 24 hours, the patient is no longer a candidate for intravenous thrombolysis or mechanical thrombectomy, and other options should be explored. So we will also jump into ischemic stroke management of post-thrombolysis. So there's a couple of things that we should be looking for, and some of those are intensive monitoring with frequent neurological examinations, because we want to establish a baseline for the patient to see if there's any deterioration later. We will also wait for more than 24 hours prior to initiating the antiplatelet therapy or anticoagulation, and usually we do this in a setting of non-contrast CT to rule out hemorrhagic transformation. And lastly, there's a strict blood pressure control, and we do this in order to decrease the risk of hemorrhagic transformation, to keep the blood pressure less than 180 over 105 millimeters mercury. At the same time, we want to avoid ischemia to the penumbra that is delivering the oxygen and the glucose in order to support the structures, and for that we want to avoid hypotension to maintain the perfusion at the collateral vessels. I also want to discuss briefly the complication of thrombolysis, and this includes intracerebral hemorrhage, as well as bradykinin-mediated angioedema and systemic bleeding. So we are returning to this subject of the penumbra, so always remember the penumbra and why it's important. And from my research, I identified that it is mainly important because of this formula. So cerebral perfusion pressure is equal to mean arterial pressure minus intracranial pressure. And when we take a look at these parameters, we know that originally when a stroke occurs, there is swelling within a structure that is enveloped within a skull. So this pressure cannot really be escaped anywhere. So then therefore, if we take a look at brain swelling, so the intracranial pressure will begin to climb due to a couple of a couple of factors. Some of that being general brain swelling, which occurs due to cytotoxic and vasogenic edema. And usually within the 4 hours that we are considering thrombolysis therapy, there is a bradykinin angioedema that is associated with thrombolysis. And lastly, within the 4 hours to a couple of days, there's a very strong chance of hemorrhagic transformation that will contribute to this intracranial pressure. So we want to know that if this intracranial pressure rises, we actually have a very delicate balance between the perfusion as well as the intracranial pressure that is rising within the skull. So within those 4 hours, here's an image of a stroke which occurred right here. And I believe this is within the region of the MCA. Within a couple of hours, let's say 4 hours to a day, there could be a hemorrhagic transformation. Now, once again, the skull is an enclosed structure, so therefore there's going to be edema and also increased pressure that's going to be climbing out of this region. So therefore, coming back to this formula, if we have increased intracranial pressure, by deduction, we know that we're going to actually have decreased cerebral perfusion pressure. And that is actually dangerous because more tissue can potentially die. So we do come back to this last slide, and we take a look at the mean arterial pressure that we want to monitor over the next couple of days after the stroke. And the reason for that is because we can still deliver blood flow to the penumbra. So here we have collateral blood flow that is going to be coming from the ACA, which is going to be penetrating the penumbra, but also some parts of the infarct core. So then therefore, it is important to keep the mean arterial pressure high. So we do allow for permissive hypertension. So in this case, the blood pressure target is less than 180 over 105 to 110 diastolic millimeters mercury. And the systolic blood pressure should be kept between 140 to 180 millimeters mercury. And I think that summarizes my presentation. Hopefully you learned a lot about the penumbra and why it's important. And of course, if you have any questions, I'm more than happy to answer them. And if there's a day that I need to come in and do so, I'm more than happy to do that as well. All right, take care for now. Bye-bye.